Okay, 6.3 is on Taylor and Maclaurin series. We're going to finish out our chapter on power series here, chapter 6. So 6.3 is on Taylor. Okay, Taylor and Maclaurin series. Okay, so how do we take a function and make a power series out of basically any function? Is there a way to do it? And there is. There's a systematic way to take any function and turn it into a power series. Okay, so theorem. Okay, if f has a power series representation, we'll say f of x, has a power series representation. Okay, not all functions will, but if it does, okay, at a value a, that is if f of x is equal to the sum of n equals 0 to infinity of some constant n times x minus a to the nth power, where the absolute value of x minus a is bounded by the radius of convergence. Okay. Then its coefficients are given by the following formula. Okay, C sub n is equal to the nth derivative of f evaluated at a over n factorial. Okay, where f to the parenthetical n power of a is the nth derivative at a. I should say nth derivative of f at a. Okay, it's the nth derivative of f at a. Okay, so if we have this power series, n equals 0 to infinity of c sub n x minus a to the nth power, that's my power series. The coefficients are going to be f of a over 0 factorial times x minus a to the 0 power plus f prime of a over the first factorial, 1 factorial, x minus a to the first power plus f double prime of a over 2 factorial x minus a to the second power plus, and it just kind of goes on forever. Okay, so we can generate a power series based on a function by using this algorithm, this recipe, so to say. Okay. Okay. The Taylor series. The Taylor series of a function centered at f the Taylor series of a function f centered at a is the summation, okay, of n equals 0 to infinity of f of n's derivative evaluated at a all over n factorial times x minus a to the nth power. This will give f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a squared minus a squared plus f triple prime of a over 3 factorial times x minus a cubed plus, and it just goes on forever. Okay, so we took this general idea of this power series. We then evaluated these at a value of a, okay, and we call that a Taylor series. Okay, plugging in what these coefficients would be. Okay. Okay, the Maclaurin series is a little bit nicer of a series. It's not centered at a, it's centered at 0. So the Maclaurin series, a little easier to work with, of the function f centered at 0 is the summation n equals 0 to infinity of the nth derivative evaluated at 0 over n factorial x to the nth power. Notice that a is 0 basically here. We're just taking, for the Maclaurin series, we're taking the Taylor series and we're just including, letting a equal 0. Okay, so for the Maclaurin series, letting that a value be 0, it's centered at 0 instead of just some random value a. It's like the Taylor series is the bigger sphere and the Maclaurin series is the smaller sphere. We can make a Taylor series out of some random function if it has these derivatives. Okay, and we could center it at a. However, we could let 0 be the value that we do this around, which makes things a lot nicer. It cleans things up a lot easier and gives us a nice series that we can work with, okay, to do other fun stuff. Okay, so this guy is equal to f evaluated at 0 plus f prime evaluated at 0 plus f double prime evaluated at 0 over 2 factorial x squared plus f triple prime evaluated at 0 over 3 factorial x cubed plus f to the 4th degree, so f to the 4th derivative, I should say, all over 4 factorial x to the 4th power plus dot, dot, dot. And this goes on forever. Okay, that's the Maclaurin series. Okay, so I'd like to work with a Maclaurin series here. Okay, as my first example. Okay. Number 1, find the Maclaurin series for e to the x. Okay, find the Maclaurin series for e to the x. Okay, f of x is equal to e to the x. So let's find the derivatives of e to the x. Well, the derivatives of e to the x are e to the x. So f prime of x is e to the x. F double prime of x is e to the x. F triple prime of x is e to the x. And the fourth derivative of x is also e to the x. That's kind of nice. They're all derivatives of each other. Okay, they are their own derivatives. Okay, so now let's evaluate each of these at 0. Well, this gives me e to the 0, which is 1. This gives me e to the 0, which is 1. This gives me, oops, the second derivative evaluated at 0 is e to the 0, which is 1. You can kind of see where I'm going here. These are all going to be 1. So f to the fourth derivative of 0 is equal to e to the 0, which is 1. Okay, so let's plug this in. Okay, so e to the x is equal to f evaluated at 0. Well, that's just 1. Okay, maybe I'll write the whole thing again. F of 0 plus f prime of 0 plus f double prime of 0 over 2 factorial plus, sorry, this is times x, plus, this is x squared, plus f triple prime of 0 over 3 factorial x cubed plus, okay, dot, dot, dot. Maybe we'll go to the fourth one here. F to the fourth derivative evaluated 0 over 4 factorial x to the fourth plus dot, dot, dot. Okay. So now we're going to plug in all of these functions evaluated for 0. Well, what are all these functions evaluated for 0? They're just 1s. So e to the x is equal to 1 plus 1 times x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the fourth plus dot, 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 forever. Okay, so let's clean this up a little bit more. 1 plus x plus, I'm going to go x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial plus, okay, and is there a way to write this as a power series? Well, if we think about this guy here, 1 as x to the 0 over 0 factorial, and x as x to the first over x or 1 factorial, okay, again, maybe I'll do that in a second row. Just, I don't want to confuse anybody. This is going to be x to the 0 over 0 factorial plus x to the first over x factorial plus x to the second over, sorry, not x factorial, this is 1 factorial, x to the second over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial plus dot, dot, dot. Can you see the pattern here? What would the series be? As I start with n equals 0 to infinity, well, what would the series take on? What's the nth term going to be? What's a sub n? Plus dot, 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 x to the nth over n factorial, right? Isn't that the nth term? So wouldn't this just be x to the nth over n factorial? Okay, that's e to the x. Okay, so this is the Maclaurin series for e to the x. Okay, we can write it as e to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial plus dot, 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 plus x to the n over n factorial plus dot, 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 okay, is equal to the summation n equals 0 to infinity of x to the nth over n factorial. Okay, I posted some common some common Maclaurin series, okay, as we go through today's lesson. You will be able to use this on the exam. So go back to sharing my screen here. So if we go here, okay, and go into a Canvas, I shared with you some common Maclaurin series. Okay, and we could generate all of these if we really wanted to. So common Maclaurin series, here we go. Okay, and so hopefully it brings up the file. Okay. Okay, and it gives me the radius of convergence as well. Okay, and we have 1 over 1 minus x, 1 plus 1 x plus x squared plus x cubed forever. E to the x is x to the nth over n factorial, 1 plus x over 1 factorial plus x squared over 2 plus x cubed over 3. Okay, sine x equals this guy here. It's an alternating series. X minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7th. Those are the odd values. The cosine are the even values. Alternating series, 1 minus x squared over 2 plus x to the 4th over 4 minus x to the 6th over 6. Okay, inverse tangent. Okay, x minus x cubed over 3, x to the 5th over 5, x to the 7th over 7. We actually generated a few of these before. We have natural log of 1 plus x, okay, is x minus x squared over 2 plus x cubed over 3 plus minus x to the 4th over 4. And then the binomial here is the summation of n equals 0, k choose n, x to the nth power. So, and I think we're actually going to derive that one in class today. Okay, the kind of the power series for a binomial. Okay. Yeah. Okay, let's look at a couple more examples here. Okay, so hopefully everybody will have this and have access to it. How would we get inverse tangent? How did we get inverse tangent before? That was through differentiation, I believe, right? And then inverse tangent, we also did through integration. However, you could use this process of integrating or just successive derivatives to get these power series as well. These are and just let them be evaluated at 0. Okay, so we could go through inverse tangent, which we have done already, but we did it using differentiation, I believe. Yeah, we did. Oh no, we did integration to find the inverse tangent function, and we used differentiation to find the natural log function. Okay. Okay. So Actually, we ended up using integration for both of these. One just 1 over 1 plus 1 over 1 plus x, and one was 1 over 1 plus x squared. So we integrated both of those to get the tangent and matrolog functions. Okay, however, we could do this process of taking successive derivatives and then plugging it in as a Maclaurin series to get the inverse tangent and the natural log as well. Okay. Okay, let's go back to the notes. Okay, so letting x equal 1 to the Maclaurin series for e to the x gives us a way to find successive approximations of e. Okay, so you're like, well, what is e? E is, remember that 2.71828, 1828, 90, 45, 90, right? Like it goes out, right? So if we take, okay, x equals 1, we get e to the first power is equal to 1 plus 1 plus 1 squared over 2 factorial plus 1 cubed over 3 factorial plus 1 to the 4th over 4 factorial plus 1 to the 5th over 5 factorial plus we could just keep going on forever here. And calculating successive digits of pi or successive digits of e, this is how it's done. It's done with a power series. Okay, for e, we can say, oh, okay, for e, it's this power series. We just keep adding on successive terms. Okay, and this comes out to be e of approximately, right, 2.718281828 45 90 45. Okay. And again, there's a mnemonic device to knowing, what is this, 13 digits of E or something like that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16 digits of E. So how do we know 16 digits of E? There's a mnemonic device that says Jackson carried a pair of Colt 45s until he was 90 years old. So Jackson carried a pair of Colt 45s until he was 90. Okay. Okay, so 1828, Andrew Jackson was the president of the United States. Okay, he carried a pair of Colt 45s. Why? Because he actually was in a duel before he became president. He's the only guy to shoot someone. You could actually duel people, I guess, back in 1828. I don't know, 200 years ago, people were kind of, I don't know, out of their mind. So you could actually challenge someone to a duel, and he did. He got shot, but the other guy died. This was before he was president, and so he always kind of like carried that persona that you don't want to mess with Andrew Jackson, because he'll just shoot you. And so, yeah. So he survived a duel, and we use him in our mnemonic device to get 16 digits of E. Okay, but if we continue to add on terms, we're going to get successively better and better approximations of E, and we're just going to 1 to the, right? So 1 to the 6, these are all ones. I'm sorry. Yeah, 1 to the 6, these are all ones. So this goes plus dot, 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 right? And this is just going to be equal to 2 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus 1 over 5 factorial plus 1 over 6 factorial plus, and it just keeps going forever. Okay, and so we can use this algorithm, this recipe, to get better and better and better approximations for E. And early on in the computing days, and sometimes even as recently as the 1990s, this was how people tested how powerful their computers were, how fast they were. They would just sit there and try to calculate successive digits of some irrational number like E or radical 2 or pi, plug it into this kind of, churning out numbers, and you could test your processing speeds based on how fast you can get digits of E to be processed. And that was how up to the 90s they tested their processing speeds. Now it's all networked. It's how fast can you send data from one place to another and then download it and upload it is all. Once the internet came on board in the 90s, it had a different metric. But for about 40 years there, between the 1950s and the 1990s, this is how people gauge their processing speed, was churning out these power series, saying, oh, and I got the digits of E to the millionth place accuracy, right? It's like, I got it to, the 100 millionth place accuracy. I got it to the trillionth place accuracy. I got it to, it was a fun game for computer programmers back in the 60s and 70s to say, oh, I built this processor and it's this fast. So anyway, a little history of processing and a little history of Andrew Jackson, especially, given what's going on. So, T sub n, I want to look at T sub n. What is T sub n of x called? Okay, and this is the nth Taylor polynomial. Okay, so T sub n is T sub n of x equal to, I equals 0 to infinity of f to the ith derivative of a over the ith factorial times x minus a to the ith power Okay, and again, this should not go to infinity. This should go to n. I'm sorry. That's my bad. Okay, because we want to stop at n. Okay, and so this is going to go to I all the way to n, which is equal to f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a squared. Okay, plus dot 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 plus, and it will end at the nth derivative evaluated at a all over n factorial times x minus a to the nth power. Okay, and this will be the, this is called the nth degree Taylor polynomial. Okay, of f at a. Okay, think of it as a nth partial sum. Okay, think of it as the nth partial sum of the series for a given f, for for a certain function. Okay. So we can get, oh, I have the 10th, 10th degree Taylor polynomial of E. And that would give me a certain approximation of E. It's never going to be exact, but it's going to be a better and better approximation. The higher the degree of my polynomial, the better an approximation I get. Okay. Our n of x is called the remainder of the Taylor series. Oops, Taylor's capital T. Okay, remainder of the Taylor series. Underlined remainder here. Okay, so that f of x is equal to the nth Taylor polynomial plus the r sub n of x. Okay, so both of these, okay, make up f of x. Okay, so again, let's think of this, in terms of, so for instance, we would say that e to the x is equal to t sub 10 of x plus r sub 10 of x. And so this would be the sum of the first 10 digits, first 10 terms. It actually is sum of the first 11 terms, I should say. Sum of first 11 terms of the Maclaurin series. This would be the remainder, or the error on my estimate. That's the error on my estimate for what exactly E is. Okay. Okay, and this is as long as the limit as n goes to infinity of r sub n of x is equal to 0. As long as r sub n gets smaller and smaller and smaller, as I get increasingly bigger and bigger, add bit more and more terms to my Taylor polynomial, r should get smaller and smaller. If that's true, then this thing works out. Okay. Okay, let's go on to example 2 here. A lot of theory. Let's see how the theory plays out. Okay, example 2, find the Taylor series for f of x equals e to the x at a equals 2. A equals 2. Okay, so at a equals 2 here. Okay, so what are we talking about? The Taylor series for f of x at x equals e to the x at a equals 2. Well, we're not doing a Maclaurin anymore. We're doing a Taylor. Okay, so what's this thing going to look like? Well, f of x is going to be equal to f of 2, okay, plus f prime of 2, okay, over 1 factorial, which is just 1, okay, times x minus 2 plus f double prime of 2 over 2 factorial x minus 2 squared plus f triple prime of 2 over 3 factorial x minus 2 cubed plus dot dot dot, and we're just going to go like that forever. Okay. So what do we get here? Well, let's take these successive derivatives and see what will transpire. So f of x is equal to e to the x. Okay, so what's f of 2? That is equal to e to the 2. Okay. And then what is f prime of x? It's also e to the x. So f prime of 2 is also e to the second power. F double prime of x is equal to e to the x, and that's f double prime of 2 is e to the second power. I can hopefully see where I'm going here. With this, e to the x is f triple prime of 2 is equal to e to the 2. Okay, and okay, we could probably stop there. Okay, so we know that f of x is equal to e to the 2 plus e to the 2 times x minus 2 plus e to the 2 over 2 factorial x minus 2 squared plus e to the 2 over 3 factorial x minus 2 cubed plus dot, dot, dot. Okay. Okay, so what is this giving me? Okay, I'm going to kind of show what this is going to sum up to. Okay, if I go n equals 0 to infinity, this is going to be, okay, e to the second times x minus 2 to the nth power all over n factorial. Okay, I can sum up, that's the power series. This is the power series for this thing. Okay, so it's this guy here, power series. That's the Taylor polynomial. But why would anyone in their right mind do this process? Okay, what's the point? And the point is that it's a lot easier to work with a polynomial than it is to than some of these inverse tangents or natural logs or exponential functions. It's a lot easier to work with a polynomial. And if we can get polynomial approximations, okay, if we can get polynomial approximations, then we can work with them rather easily and nicely. Okay, back when they were developing this stuff, almost 300 years ago, okay, maybe 250 years ago, maybe, not 300? I don't know. I don't know. 1680s, whenever that is. Okay, well, 350 years ago? Okay, so yeah, about 350 years ago when they're developing this stuff. Okay, they didn't have computers or calculators or any of those modern conveniences that we use, to probably take for granted so much. Okay, so what they had to do all this stuff by hand. They do all the calculations by hand. Usually they would pass it off to someone who had, a lot of time on their hands, like, Catholic monks would do a lot of this number crunching. And so, because they would just pray and do math and pray and do math, and that was their day. And so, they would make these anthologies of just tables and tables and tables of numbers. If you like, oh, I want e to the 10th decimal place, you'd have to like scroll through and all of these books, all these bound things that just said, oh, well, this is what e is to the, this is that accurate decimal place accuracy. And then I go to the next decimal place, and then I go to the next decimal place, and then I go to the next, and you have these lists and lists and lists of just numbers being crunched, And so this was kind of how they did it. They used calculus to, get better and better approximations of all these transcendental numbers. Okay, all these numbers that go on forever. Okay, and so again, we get better and better approximations. If we take, say, I don't know, t sub 5, okay, of x here, what is that going to give me? That's going to give me e squared plus e squared x minus 2 plus e squared over 2 factorial x minus 2 squared plus e squared over 3 factorial x minus 2 cubed plus e squared over 4 factorial x minus 2 to the fourth plus e squared over 5 factorial x minus 2 to the fifth. And that's it. We can stop there because we've hit our fifth power. Okay, t sub 5 actually has 6 terms. Okay, we can actually factor out the e squared because they all have that in common. So t sub 5, so e to the x, okay, t sub 5 of x is equal to e squared times 1 plus x minus 2 plus x minus 2 squared plus x minus 2 cubed. I'm sorry, x minus 2 squared, this should be over 2 factorial, over x minus 2 cubed over 3 factorial plus x minus 2 to the fourth over 4 factorial plus x minus 2 to the fifth over 5 factorial. Okay, so now what I'm going to do is I'm going to kind of use our modern conveniences of the computer to show exactly what's happening here. And you'll see, that's kind of interesting. Okay, hopefully your takeaway will be like, oh, wow. So they did all this stuff by hand, and we actually get to see it in a millisecond unfold for us. Okay, the magic of our modern computational abilities. Okay, so let's go here to Desmos. Okay, and see what exactly is happening. And so, where's my Desmos? There it is. So if I plug in, okay, okay, y equals, I want lowercase y equals, okay, e to the x. I want e to the x power. Let's raise this bad boy to the x power. Boom. Okay, we get this guy here. Okay, right? Okay, so let's now look at our Taylor polynomial and see what happens. Okay, when I start adding successive terms here. Okay. Let's start adding more and more terms to our Taylor polynomial. We have y equals, okay, y equals e to the second power. We'll start there. That's our first term. E to the second power. Okay, and what does that create? That creates a line. It creates a blue line. Okay, not a good approximation. Okay, to e of x. Okay, but let's continue this. Let's add in some more terms. We added the one term here. Now let's add the next term. Okay, what was the next term? Okay, in my Taylor polynomial. Oh yeah, that was x minus 2. Okay, and then we can kind of see what happens here. It's right at, it's now a line. It's a line. I want to know what happens, okay, when x is at x equals 2. So let's put in the x equals 2 line. I'm going to make this a dashed line if I can. How do I do that? Right click? Nope. There should be a way. Hold down. Yeah. I'm going to make this a dashed line. Okay. We're really interested in what's happening at x equals 2 because, okay, because this is the Taylor polynomial centered around x equals 2. Right? Let me actually pull this down a little bit. Okay, so we get a better and better idea of what's happening around x equals 2. Okay. Okay. What's happening around this center, this point of intersection, x equals 2. Okay, for e of x. Okay, now let's put in another term of accuracy for again, I want to pull this down a little bit. Of accuracy for just a little bit. Okay, for the next term here. Let's go to the next term. What should the next term be? Plus what? X minus 2
Squared.
Yeah, squared, exactly. Raised to the second power. Ooh, look at that. Okay. So now what is this? This is a parabola. And do you see how the blue line and the red line are hugged very tightly? They're almost indistinguishable around x equals 2. Okay, very cool. So now let's add the next one. This is going to be x minus 2 to the what?
So the third.
Yeah, to the third. Let's see what happens when we do third there. Oh, interesting. Interesting, even more interesting. Look around 2 here. Very much indistinguishable. You can see how this is a cubic. It goes, and then here it starts hugging this, goes a little bit above E, and then a little bit below E, and then it kind of goes back, and it hugs that pretty closely around 2.
I had a question real quick.
Oops, 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 oops.
You can hit undo, I'm pretty sure. Like it's above the, yeah,
Thank
there
you.
you go. Well, why don't you put it over the factorial here?
Oh, sorry. I should be putting it over the factorial. I always forget that. Okay, thank you. Yes.
Yeah.
Okay. Divided by 2. Okay, there. It should be, yes. Okay, and then this will be divided by 6. Okay, now we have a much better, yes, much better. It's like, I wonder why it's not hugging that. It's going to hug it even closer. Okay, thank you for that. I don't know why it slipped my brain. Okay, let's go to the next one, which would be x minus 2. X minus 2, whoops. Okay, raised to the 4th power divided by, oops. Okay, divided by 24. Okay. Okay, what do we see here? We see that around x equals 2, there again, the curves are basically indistinguishable. Okay, all the way up. We could zoom out a little bit maybe. And we could see that all the way up here for very, very far. Okay, the curves are basically indistinguishable. Okay, and that's only what, 5? That's only 5. Gosh darn it. Stop. Just want to go inside. Okay, that's only 5 terms so far that I've added. Let's add the 6th term here. Okay, plus, okay, x minus 2. Okay, raised to the 5th power. Okay, over, this is 120. Okay, and then we'll kind of stop there because it just gets silly after this. The accuracy gets really, really good. Okay, and you can see that E and that polynomial are basically indistinguishable after, very small value of x. Does this make sense? Does this make sense what's happening here? Right, we're using this polynomial to approximate E, and it's really, really good at doing that. Okay, especially for positive values of x. Does that make sense? Okay. And thank you again for that one catch. Okay, let's go back to the notes. Okay, and let's calculate. Let's calculate. Yeah, up that. There we go. Hit a key accidentally. Okay, so let's go back and calculate the Maclaurin series for sine and cosine. Okay. So let's find. Okay. So yeah, so we got that. And number 3. Okay, find the Maclaurin series for sine. Okay, let's find the Maclaurin series for sine. Okay, so f of x is equal to sine x. The first derivative of x is equal to cosine x. The second derivative of x is equal to negative sine x. The third derivative of x is equal to negative cosine x. The fourth derivative of x is equal to sine x. And it just keeps going on like this. The fifth derivative of x is equal to cosine x. The sixth derivative of x is equal to negative sine x. The seventh derivative of x is equal to negative cosine x. And the eighth derivative of x is equal to sine x. Okay, so what happens if I evaluate these at 0? Okay, f of 0 is equal to 0. F prime of 0 is equal to 1. F prime double prime of 0 is equal to 0. F triple prime of 0 is equal to negative 1. F to the fourth derivative of f evaluated 0 is equal to 0. Okay. And then the fifth derivative evaluated at 0 is equal to 1. The sixth derivative evaluated at 0 is equal to 0. The seventh derivative evaluated at 0 is equal to negative 1. And the eighth derivative evaluated at 0 is equal to 0. Okay. So let's plug this into our Taylor series. Okay, we know that f of x, or sorry, not our Taylor, our Maclaurin series. Our Maclaurin series is f of x equals f of 0 plus f prime of 0 plus f double prime of 0. I'm not going to forget the factorial this time. Okay, x. Oh, this is, I forgot the x. Great. Okay, x squared plus f triple prime of 0 over 3 factorial x cubed. Okay, plus f, okay, to the fourth derivative of 0 over 4 factorial x to the fourth plus dot, 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 dot. Okay. I really want to go up to the 8th derivative, okay? But I'm not going to write all those terms. I will eventually show you what they are. But notice that every other term will go to what? Every other term is going to go to what?
0.
0. Thank you, Corey. Yes, absolutely. So every other term is going to go to 0. Okay, so this is going to be 0 plus 1 times x plus 0 plus negative 1 over 3 factorial x cubed plus 0 plus 1 over 5 factorial x to the fifth plus 0 plus negative 1 over 7 factorial x to the seventh plus 0. Everybody get that? Okay, and what is this? This is the sine of x. Okay, so the sine of x is actually x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And that's an alternating series. Okay, it's an alternating series of the odd powers. Okay, so how do we generate odd numbers? Well, we can say this is n equals 0 to infinity of -1 to the nth power, x to the 2n plus 1 all over 2n plus 1 factorial. And that is the power series for sine. Okay, now I could do the same process to find cosine if I really wanted to, or I can be a little sneaky. Okay, so let's be a little sneaky, because what's the derivative of a sine? Not everybody at once.
Cosine.
There you go, cosine. Okay, yes. The derivative of sine is cosine. So what would happen if I just took the derivative of every term of sine? That should turn it into cosine. So let's find the Maclaurin series for cosine x. Okay, let's find the Maclaurin series for cosine x. Okay, so d dx of sine x is equal to cosine x. Okay, so d dx of sine x would then be equal to the derivative of the power series x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial minus x to the 11th over 11 factorial plus ... forever. Okay. So let's take the derivative term by term. The derivative of x, that is 1. The derivative of x cubed over 3, that is 3x squared over 3 factorial. Okay. X to the 5th, that's 5x to the 4th over 5 factorial minus 7x to the 6th over 7 factorial plus 9x to the 8th over 9 factorial minus 11x to the 10th over 10 factorial plus, okay, oh, sorry, this is 11 factorial. Okay, 11 factorial, okay. So I don't think we need the parentheses anymore. Okay, but what will happen to these factorials on the bottom? Remember, what is 3 factorial? 3 factorial is 3 times 2 times 1. So wouldn't the 3 and the 3 cancel? Right? And the 5 would cancel, leaving me with a 4 factorial. This leaves me with a 2 factorial. This leaves me with a 4 factorial. The 7 and the 7, that leaves me with a 6 factorial. This leaves me with a 8 factorial. This leaves me with a 10 factorial. And so when it's all said and done, we get the cosine of x is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial minus x to the 10th over 10 factorial plus ... So what is this? These are the evens, right? These are the evens. Okay, so the cosine of x is equal to, okay, the summation of n equals 0 to infinity of an alternating series, -1 to the nth, of x to the what? 2n over 2n factorial. Okay, and that's the power series for cosine of x. Actually, I'm going to write it all together. I'm going to write this as the cosine of x is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot, dot, dot is equal to the summation n equals 0, negative first to the n, x to the 2n over 2n factorial. Okay, number 5. Find the Maclaurin series for f of x is equal to 1 plus x to the k power. Okay, so this is a binomial. Okay, binomial to the kth power. How can we find the Maclaurin series, a power series for this particular binomial? Okay, binomial to the kth power. Okay, so we have f of x is equal to 1 plus x to the kth power. Okay, so what would f of 0 be? That would just be 1 plus 0 to the kth power, which is 1 to the kth power, which is 1. Okay, interesting. Okay, what's the derivative? F prime of x is k times 1 plus x to the k minus 1 power. So what's f prime of 0? That's going to be k times 1 to the k minus 1th power, which is just k. Okay, the 1 to any power is just 1. The second derivative is going to be k times k minus 1 times 1 plus x to the k minus 2 power. So f prime of 0 here is going to be k times k minus 1 times 1 to the k minus 2 power, which is just k times k minus 1. So hopefully you can see the pattern developing here. We'll do one more. What is the third derivative? That's k times k minus 1 times, bring the k minus 2 down, times 1 plus x to the k minus 3. F prime of 0 is equal to k times k minus 1 times k minus 2 times 1 to the k minus 3 power, which is just k times k minus 1 times k minus 2. Okay, and that is okay. Okay, so what would be the nth derivative? Let's continue this pattern down here. What would be the nth derivative? F to the nth derivative of x equals what? Well, it would be k times k minus 1 times k minus 2 times k minus 3 multiplied all the way to k minus n minus 1, because it's one less. Okay, than the derivative. Okay, the third derivative produced a k minus 2. So the nth derivative would produce a k minus n minus 1. Okay, times 1 plus x to the k minus nth power. F sub n of 0 is equal to k times k minus 1 times k minus 2 dot 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 all the way to k minus n minus 1. Okay, so let's say what the power series for this thing would be. 1 plus x to the kth power is equal to, okay, plugging in for f sub 0, this is, again, this is f sub 0, right? So maybe we'll back it up just to make sure that we know f sub x is equal to f sub 0 plus f prime of 0 x plus f double prime of 0 over 2 factorial x squared plus f triple prime of evaluated 0 of 3 factorial x cubed plus dot, dot, dot. It kind of goes on forever. Okay. And so what is 1 plus x to the kth power then? Well, what is f sub 0? That's just 1. What is f prime of 0? That's just kx. Okay. What's f double prime of 0? That's k times k minus 1 all over 2 factorial x squared plus k times k minus 1 times k minus 2 all over 3 factorial x cubed. Okay, plus dot, 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 plus, let's go to the nth term. Okay. What would the nth term be here? Okay, plus k times k minus 1 times k minus 2, k dot, 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 times k minus n minus 1, all over n factorial x to the nth, and then we would continue on forever. I just want to make sure we have that nth term in there. Okay, this would continue on forever, but we now can isolate the nth term here. Okay, well, we have something for this pattern here, and it comes to us from probability. Okay, and binomial probabilities operate based on this type of a pattern where we say out of k items, choose n of them. This is equal to the notation out of k items, choose n. And this is k factorial over k minus n factorial divided by n factorial. Okay. And this will equal the coefficient of my nth value. Okay, so this is going to be k times k minus 1 times, because what is k factorial? Isn't that k times k minus 1, right? Times k minus 2 times k minus 3 times dot, dot, dot times, I'll bring this all the way to the next term, the n plus 1th term, so you can see how this is going to cancel out. Everything below k minus n is going to be gone, okay, on the top, and then just n factorial will be left on the bottom. This is going to be k minus n minus 1. The next one is going to be, the next value here is going to be k minus n, and then it'll go to k minus n plus 1. Okay, and then this will go all the way to okay, this will go all the way down to 3 and then 2 and then 1. Okay, so we'll go all the way down to 3 and then 2 and then 1. Okay, all over, well, k minus n. Well, I'm going to put that k minus n factorial here. I'm going to actually expand k minus n factorial to k minus n, k minus n plus 1, okay, which is k minus 3, k minus n plus 1, k minus n plus 2, okay, all the way down. Okay, so if I get to 3 and then 2 and then 1, all of these are going to cancel out. Okay, so the closer I get to k, okay, as n approaches k, okay, I'm going to get them all to cancel out. And so this will just leave me with an n factorial on the bottom, okay, which is exactly what we have here. So we can say that 1 plus x to the k power okay, is equal to, okay, the summation, well, let's do it this way. 1 plus kx plus k times k minus 1 over 2 factorial x squared plus k times k minus 1 times k minus 2 over 3 factorial x cubed plus dot 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 forever is equal to the summation of n choose k as n equals 0 to infinity of n choose k. That's my coefficient. My coefficient here for each of these is n choose k. N choose k, n choose k. Okay, whatever value, whatever polynomial you want to go to, okay, for k, it's just going to be n choose k, okay, out of n items, choose k of them, okay, and then this is going to be times x to the nth power. So we get a nice formula for the polynomial approximation to a binomial expansion. Okay, so say k was to the 50th power, you could approximate 1 plus x to the 50th power by doing this basically binomial expansion and have, 51 terms, or you would actually, you'd have an infinite number of terms, but you would just keep getting increasingly closer and closer values to, what this, polynomial would be. Okay. Okay, and that is section 6.3.